Hello everybody. In the last video, we discovered our fourth and our final conic, the hyperbola, and we derived an equation for it. Hyperbolas look a lot like parabolas, except there's two of them that either face outward or up and down. They look a lot like parabolas, except the key difference between these shapes and parabolas is parabolas don't have asymptotes, while hyperbolas do. Now, we also defined a few lengths for the hyperbola. The first thing I should talk about is what we mean as the center of a hyperbola. The center of a hyperbola will be the location where the two slant asymptotes intersect, so this is where the center will be. And the distance from the center to what we're going to call the vertices of the hyperbola, we're going to define this length here, A. And since the origin is always going to be halfway between the two foci, it'll also be halfway between the two vertices. If this distance is A, this distance will also be A. The distance from the origin to one of the foci is what we defined as C. And again, because of symmetry, if this length is C, this length here will also be C. And we also could have the situation where the foci are not along the x-axis. They could also be along the y-axis. Okay, I guess one thing to notice in a similarity between these shapes and the parabola is the foci will always lie inside of this shape here. So remember, for parabolas, the foci lie inside of the parabola. For here, the foci, for hyperbolas, the foci will lie kind of inside of the hyperbola. Now, we also derived an equation for these, and there was two of them. There was one of them that was an x squared over a squared minus a y squared over b squared will be equal to 1. Or we had a y squared over a squared minus an x squared over b squared would be equal to 1. So there are really two main questions I want to answer in this video. One, if we were just presented with one of these two equations, how would you know which version it is? And the other thing we want to think about is, while we can see what the A represents, and A represents the distance from the center to the vertices, what the heck is this B? We don't see it in the picture. At least we know where B came from. When we derived the equation of the hyperbola, we ended up getting this thing that was a c squared minus an a squared, and we said, oh, that looks ugly in the equation, we'll just call it b squared. So all we know is that b squared is the same thing as c squared minus a squared. Here's a nice formula, but where does it appear in the pictures? And so those are the questions we want to answer. Presented with one of these two, how do we know which shape it goes with, or what's the correct orientation if you're presented with one of these? And what the heck does B tell us in the picture? Okay, so I'm going to go ahead and erase a little bit of this here. Let's first answer the orientation question. Okay. If we're presented with an equation of a hyperbola, how do we know if it opens up outward, or left and right, or up and down? So really, that's what the A value is going to tell us, or where the location of the A is. So to kind of answer that question about orientation, let's ask, what does A tell us about the hyperbola? The answer is it tells us all about intercepts. It tells us about intercepts, which will help us understand orientation. Okay, let's say that someone presented you with x squared over a squared minus y squared over b squared is equal to 1. Okay, we want to know, does it open up left and right, or up and down? Okay. What's going to help us is to think about intercepts. Okay. So where the graph crosses the y-axis, this is what we call the y-intercept. Where the graph crosses the x-axis, this is what we call the x-intercept. So when I'm looking at something like this, I'm just going to ask myself, Does this hyperbola have x-intercepts or does it have y-intercepts? So here's kind of a sub-question. Let's ask ourselves, does this have y-intercepts? Let's ask that first. Y-intercepts? I don't know. Let's see. Okay, if this had y-intercepts, what would be true? What's true in general about a y-intercept? Well, notice for a y-intercept, we always know one of the coordinates of the y-intercept. Y-intercepts have an x-coordinate of 0. So for a y-intercept, this is when x is equal to 0. So let's try to solve for a y-intercept if this even has y-intercepts. Okay, so plugging in x equals 0, we're going to get 0 squared over a squared minus y squared over b squared will be equal to 1. Okay, here we're going to get a 0 squared over a squared. We have a 0 in the numerator and a non-zero number in the denominator. This piece right here will just be 0. So this will just be 0 minus y squared over b squared will be equal to 1. Or we'll just have a negative y squared over b squared will be equal to 1. So let's attempt to solve for the y-coordinate of the y-intercept. Okay, so if we attempt to do that, how can we solve for y here? Well, it might be nice to clear the fractions. Let's multiply both sides by, you can either multiply both sides by b squared or negative b squared. Let's multiply both sides by, how about let's multiply both sides just by b squared. Okay. If we multiply both sides by b squared, these will cancel. And we'll be left with a negative y squared is equal to b squared. Okay. So let's ask ourselves the question, or I want you to pause the video, and I want you to ask yourself the question, does this equation right here make sense? The answer is no. This is a contradiction. This doesn't make any sense. And let's think about why. Also, if you ever see two arrows pointing towards one another, this means contradiction. Notice what this is saying. When you see a negative y squared, the square only touches what's directly next to it. So actually the minus sign here, or this negative, is not being squared. So we can read this as, how about a negative 1 times a y squared is equal to b squared? Let's actually write this a little bit lower. Negative 1 times y squared is equal to b squared. Okay, well, notice here, first of all, the b squared is in the denominator. B is non-zero. B is a non-zero value. If b was 0, notice we'd have a problem. We'd be dividing by 0. That's like the biggest no-no in math. So the right-hand side, I have a number being squared, so the right-hand side is positive. Whenever we square a number, it's positive. The right-hand side is positive. Okay, here we have a number y being squared. This is positive. If I didn't have the negative 1, we have y squared, which is positive. We're multiplying it by a negative. The left-hand side is a negative. So here we're saying that a negative is equal to a positive. Well, the only way a negative can be equal to a positive, are there any numbers such that its negative is the same as the positive? Well, the only option would be 0. The negative 0 is the same as 0. So the only possibility, the only way this could be true is if y is equal to b, which is equal to 0, but b can't be 0. B can't be 0, again, because we'd be dividing by 0. This here is a contradiction. This is a contradiction. So this makes no sense. So what is this telling us? This is telling us that there are no y-intercepts. There are no y-intercepts. So most likely, let's see if there are x-intercepts. There are no y-intercepts for this one. So I guess if you think about the two orientations we have, it being up and down or left and right, well, if it's left and right, they'll have x-intercepts. If it's oriented up and down, they'll have y-intercepts. Well, we've seen this doesn't have y-intercepts, so hopefully this should make sense that it should be the one that's facing left and right. This should have x-intercepts. And let's take a look. Let's take a look. Okay, it doesn't have any y-intercepts, but does it have x-intercepts? Okay, well, let's figure it out. What's true about x-intercepts? What's true about x-intercepts is that the y-coordinate is 0. So this is when y equals 0. So if we try to solve for it, if we replace y with 0, we're going to get x squared over a squared minus 0 squared over b squared will be equal to 1. Okay, well, 0 squared over b squared, that'll be 0 over b squared, which will just be 0. So we'll get x squared over a squared will be equal to 1. Okay, if we try to solve for the x-coordinate of the x-intercept, we can multiply both sides by a squared. Okay, so if we move this over here, well, I guess these will cancel. We'll get that x squared is equal to a squared. So now if we square root both sides, this is saying that x could be equal to, we don't want to forget the plus or minus, x could be equal to plus or minus a. This is telling us that this graph has x-intercepts when x is equal to a or when x is equal to negative a. So this must be the orientation. This must be the orientation of this equation. Notice that the x squared is the one that doesn't have a minus sign in front of it. So if I plug in 0 for y, I'll have x squared over a squared is equal to 1. I could solve for x. If x was 0, I'd have a negative y squared over b squared. If I tried to solve for y squared, I'd get a negative is equal to a positive. I'd have a contradiction. So this is saying this number out front, the one that doesn't have a minus sign on it, this is saying this has x-intercepts, which means it must be opening up this way. Now the other way around, if we do it the other way around, if we have the one that's y squared over a squared minus x squared over b squared is equal to 1. I hope you realize that this thing will not have x-intercepts. If it has an x-intercept, that's when y would be equal to 0, so this piece would get zeroed out, and you would be solving if you multiply both sides by b squared. You get negative x squared is equal to b squared. You get a negative equal to a positive. You'd have a contradiction. This thing does not have x-intercepts, but it does have y-intercepts. For a y-intercept, that's when x is 0. So if you plug in x equals 0, this piece will get zeroed out. And you would solve for y. You'd get y squared is equal to a squared. Or y would be equal to plus or minus a. So this thing has y-intercepts. This has y-intercepts. So for this version, it must be opening up and down. Okay, let's write that really quick. Okay. So for this one here, this orientation, it has x-intercepts. So this one is x squared over a squared minus y squared over b squared is equal to 1. The other orientation should write this distance here is a. From here to here is a. From here to here is a. This one is y squared over a squared minus x squared over b squared is equal to 1. This one has y-intercepts. So you're always looking for the one that doesn't have one that doesn't have the minus in front of it. This one has x-intercepts. This one has y-intercepts. And that's how I can tell the orientation. Okay, so that answers our first question, how we know what the orientation is and what the a value tells us. Now the big question here is, what does the b value tell us? That's the big mystery. What does b tell us? We're going to get a lot of good information We're going to get a lot of good information out of this. What does B tell us about the hyperbola? The answer to this turns out to be the one thing we haven't really fully studied yet, the asymptotes. So to answer this question, let's look at the asymptotes. Okay. For right now, let's go ahead and let's look at this. Let's look at the version that has x-intercepts. Okay. What we're going to try to do is we're going to see if we can derive an equation for these for these asymptotes. But to understand or derive these asymptotes, we have to know what these asymptotes are really telling us. And just like when we are studying rational equations, what the asymptotes are telling us here is about the end behavior. Notice as x is getting really big, the graph is settling on these slant asymptotes. So we should ask the question, okay, this one right here, this equation for this one is x squared over a squared minus y squared over b squared is equal to 1. We should ask ourselves is what happens when x gets really large? What is the graph settling on? We want to know what's the end behavior. We want to examine end behavior. Okay, so let's do it. So to figure out what's happening when x gets really big, we want to know what the y values are settling on. I know they're going towards positive or negative infinity, but how are they approaching positive and negative infinity? Well, to answer that question, what we're going to do is we're actually going to solve for y squared. We're going to write this hyperbola as y kind of as a function in x. It won't quite be a function in x. We'll kind of break it into two pieces, but we're going to solve for y, and we're going to see what happens as x gets really big. Let's do it. Okay, so we have x squared. So this is our math research now. So we're doing our math research. X squared over a squared minus y squared over b squared is equaling to 1. We're going to solve for y. Okay, how could we solve for y here? Okay, well, how about we subtract x squared over a squared from both sides? So we get a negative y squared over b squared would be equal to a 1 minus an x squared over a squared. Okay, then we could multiply both sides. How about by negative b squared? By negative b squared. That'll get rid of this negative and this b squared. So we'll have that y squared will be equal to, let's go ahead and distribute in this negative b squared. So we'll get a negative b squared. Now it'll be a plus a b squared x squared all over a squared. How about I do this? So the minus and the minus will make a plus. So we'll get a, how about we do this? Minus, we'll get a negative b squared times the x squared over a squared. I guess you could think of, maybe we have this 1 right here, 1 minus. Okay, so we'll get the negative b squared. A minus and a minus make a positive, so we'll do positive b squared x squared over a squared. Okay, let's clean this up a little bit more. For some reason, I don't like having this negative b plus this piece right here. I'm going to flip the order of addition. So we could write this as b squared times x squared over a squared plus a negative b squared. But if you think about this b squared as being b squared over 1, And thinking about how we multiply fractions, remember we multiply numerators and denominators? Well, and also order of multiplication doesn't matter, so I can kind of rearrange these numerators and denominators however I'd like. So for this piece right here, and there's really no reason to do this other than just kind of making it look nice, is I could write this as how about b squared. I'm going to flip the order of multiplication of the 1 and the a squared times an x squared over 1. And how about instead of an x squared over 1, oh, hold on, instead of a plus negative b squared, how about we write a minus b squared? And x squared over 1 is just x squared. So this is equal to b squared over a squared times an x squared minus ab squared. Okay, so this is what y squared is equal to. And now we're going to square root both sides. I'm going to move it up here. Okay, so let's go ahead and square root both sides, and let's not forget the plus or minus. So we'll have that y is equal to the plus or minus, the square root. We'll have a b squared over a squared times an x squared, okay, minus a b squared. Okay, so all we did here is just solve for y. All right. And again, we're going to try to figure out what happens as x gets really, 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 really big. But I guess the thing I'm noticing is there's a lot of things being squared here. And I'm hoping to factor the inside, factor some squares out, and I can move them outside of the square root and undo the squares. I'll show you what I mean. So let's write this as y is equal to plus or minus the square root. Let's see if we can factor out. It'd be nice to be able to factor out a b squared, an a squared, and an x squared. It'd be nice to be able to factor all of these out. Now I have to think about what would be left in the parentheses. Okay, I factored everything out of this term, so we should have a 1 here. So when this distributes back in, I'll get back to this piece. But when I distribute back over here, I have to be just left with a b squared. So what are we going to be left with over here? Okay, well when I distribute back in, I have to make sure that x squared cancels out. And I'd have to also make sure that this a squared cancels out. Okay, so imagine if I were to distribute this back in. When this hits here, I'll get this term times 1, which is exactly what we have right here. But when this distributes to the a squared over x squared, the a squareds would cancel out, the x squareds would cancel out, and I'll just be left with a minus b squared. So this and this are equivalent. Why this is kind of nice, really this is just kind of some playing around. We'll get plus or minus. I can move this piece outside of the square root. Recall that the square root of, maybe I'll use different letters, of m times n is equal to the square root of m times the square root of n. That's what I'm going to do here. So this will be equal to the square root of b squared over a squared x squared times the square root of 1 minus a squared over x squared. Okay. Well, all of these squareds here will get killed with this square root. So this will be equal to plus or minus. This right here just reduces to a b over a times x times the square root of a 1 minus a squared over x squared. Okay, the reason for that is if you multiply b over ax by itself, b over ax times b over ax, when you multiply this all together, you're going to get a b squared times b squared, a squared times a squared, x squared times x squared. So the square root of b squared over a squared times x squared, the square root of this will just be b over a times x. Okay. We're now in a great form, because now we're going to ask ourselves, what happens as x gets really, 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 really big? Well, notice as if x gets really, really, really big, what's happening to a squared over x squared? what's happening? As x gets really, really big, what is this doing? Let me pause the video and think about that for a second. Well, a is going to be fixed. A is a fixed number, but the denominator is getting really, 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 really large. So this is kind of like, I don't know, you took a pizza and you cut it into, I don't know, let's say maybe if a was 2, for example, then a squared would be 4. Okay, so or I don't know, maybe this, you're taking, maybe it's 4, so you're taking 4 pizzas and you're cutting it into a certain number of slices. So you're cutting into a number of pieces. You have a bunch of pizzas. You're cutting them into like 4 slices. Or if x is really big, you're taking a bunch of pizzas and you're cutting into like 100 slices. You're cutting them into 500 slices, 1 billion slices, 1 million slices, and you'd only be taking like, I don't know, maybe 4 of those. I mean, if you cut a pizza into like 1 billion slices and you're only taking 4 of them, I don't know, you might as well have no pizza. This is getting closer to 0. As the denominator gets really, 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 really big and the numerator stays the same, this thing approaches 0. That's great news! That's great news, because as x gets really, really big, this piece gets closer to 0. So this just becomes, we just get y is equal to plus or minus b over ax times the square root of 1 minus 0. Well, that's just the square root of 1, which is just 1. So we get y is equal to plus or minus b over ax. What is this? What is this? These are the equations of the asymptotes. These are equations of lines. This is like y equals mx. M is the slope. So the slope could either be positive b over a or the slope could be negative b over a. One of our asymptotes had a positive slope. One of them had a negative slope. We figured out the equations of the asymptotes. The equations of the asymptotes. I know this is a lot going on here, but we've really made a big discovery here in figuring out what b is. Let me draw the picture. So the equations of the asymptotes on a hyperbola are plus or minus b over ax. The equation of this asymptote, this is a positive slope. The equation for this will be y equals b over ax. For this one here, we'll have y equals negative b over ax. So let's think about it. Well, the distance from here to here is a. Okay? So, remember what slope tells us? This is like rise over run. So this says if we move to the right a, this would be our run. If we run a, we would rise b. So this distance here would be b. If we went backwards a, we would go up. We would go up a. Or we would go up b. So what this has, or what we've created, is something that's called the central box. The central box. Let's draw it. We have the central box. Or let's even draw it first. Let's do this. So what's great about hyperbola, what really guides the graph of a whole hyperbola, are these things called this thing called the central box. Okay, it has a half a width. We would go this way a, and we would go up b. Okay, I guess this would be negative b. This would be a, and there's this box here. there's this box. And what's great about this central box is it guides our asymptotes. The asymptotes will always go through the corners of this box. Okay, the equation of this line is y equals b over ax. The equation of this asymptote will be y equals negative b over ax. So now that we have the asymptotes, what we can do is we can now draw the graph. Well, remember that A tells us information about the intercepts. So the graph would start on this, I guess on the outside of the box, and it would now approach the asymptotes. It would approach the asymptotes. And that's how we can draw a parabola. We know what the B is, we know what the A is. You'll draw this central box, you'll draw your asymptotes. We know that A tells us about the vertices, and then we can have our parabola guide along the asymptotes. How beautiful, how beautiful. Okay, let's summarize with both pictures. Let's summarize with both pictures. So if we have x squared over a squared minus y squared over b squared is equal to 1, or if we have y squared over a squared minus x squared over b squared will be equal to 1. Okay. In this case here, what would you do if you were graphing this? You would go to the right and the left a unit, since this has x-intercepts. We'd go this way a units, we'd go this way a units. So I guess this is a, this would be negative a. Okay, then now we would go up b units. We would go up b units and we would go down b units, and you'll draw the central box. Once you have your central box, then you can draw the asymptotes. And now the graph has x-intercepts, and they'd be at negative a and a along the x-axis. So the graph hits here. This is where a vertex be. This will be another location where a vertex will be. And then you'll guide your graph to these asymptotes. So once you know the central box and you can sketch the central box, you can easily sketch these hyperbola. Okay, for the other orientation, well, this one has y-intercepts, so we would go up and down a units. So we would go up a units and down a units, and now we would go right and left b units. So we'd go right b units, we'd go left b units. You'll draw the central box. The central box will tell you about the asymptotes. The asymptotes will hit the corners of the central box, and then we can guide the hyperbola along these asymptotes. So B helps us understand the asymptotes. B helps us draw this central box. Okay, another interesting thing to think about is, remember when we did the derivation for these equations, we had this b squared, we called this b squared, what? We called it a c squared minus an a squared, a c squared minus an a squared. Okay, let's remember that. Let's remember where the foci are. So here are the foci for this one. Okay, I guess this would be over c, this would be over negative c. Over here we would be up c, here would we be down c. Okay, well, this is looking a lot kind of like a Pythagorean theorem here. Notice if we rearrange this just a little bit, we would have that c squared would be equal to b squared plus a squared. So notice here, notice that we have this triangle right here. This is telling us very interestingly, We know that this distance here is A, this distance here is B. These would be the legs of that triangle. Then C must be the hypotenuse, which is interesting that this length right here, from the center to a corner of the box, that length must be C. If you were to take this line segment right here and rotate it down, it would fit right from here to here. It would fit right from here to here. So this beautiful right triangle, I always hold on to. I always think about this right triangle when I'm trying to remember this relationship here. And it'd be the same over here. It'd be the same over here. Okay, let's see. Let's see. Well, from here to here is B, and well, from here to here is A. Those would be the legs of the triangle, and that hypotenuse would be C. Means from here to here would be C. This length here is C. If you were to take this, I didn't draw this perfectly, and rotate it, it would fall right onto the foci. Beautiful. So this is all I have to talk about in this video here. We've hopefully answered a few questions. In the next video, we're going to be doing a lot of examples, but let's summarize everything that we've learned so far in this video. What do the A's tell us? The A's tell us about the x-intercepts or the y-intercepts. Okay, this will have x-intercepts. There's no minus sign on it. This will have x-intercepts. This one here will have y-intercepts. We learned about the equations of the asymptotes. The equations for this one, well, what will they be? What will be the equations of these lines? Well, this will be y is equal to, let's maybe do it in a different color. Let's do it in green. Okay, this will be y is equal to, what's the slope of this line? Rise B, run A. Rise over run X. Now this will be the same, it'll have the same slope, but just negative. So the equation of this asymptote we discovered will be y equals negative b over ax, and that's how we get this central box. Now over here for this version, so I should write here asymptotes, will be y equals plus or minus b over ax. Okay, how about for this orientation? We have this asymptote. We have this asymptote. Okay, well, looking at this nice right triangle we discovered, well, what's the rise? The rise is A, the run is B. So this will be y is equal to rise over run. Let's make sure there's not too much in the glare. Okay, we're okay. This one right here, it'll have the same slope, just negative. This will be y equals negative A over bx. So the asymptotes for this version, the asymptotes here will be y equals plus or minus A over bx. Okay, so I know it seems like there's a lot to memorize here, but what I hope you hold on to is thinking about this central box, thinking about this right triangle. You can hopefully then from this right triangle figure out that c squared has to equal to b squared plus a squared. And also from this triangle in the central box, you should be able to figure out what the slopes of these lines are. Okay, in the next video, we're going to be getting practice with graphing hyperbola and doing those problems where if we're given some information about a hyperbola, can we find its equation? We'll see you there. Take care.